Good morning, good afternoon, and good evening. This is our fourth workshop of the year, and we want to thank you all for joining us and let you know that we greatly appreciate you taking time out of your busy day to join us. I'm Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell. Thank you all for attending Rigaku's workshop series on X-ray computed tomography. This workshop will focus on CT data analysis techniques using ImageJ. This session will be taking place in the offices with Angela and Aya reviewing in real time how to use ImageJ to process scans on a variety of sample types. Please note, if you missed any of the previous webinars or workshops, you can view them on the Rigaku website. Now, as far as today goes, this is going to be an interactive session like our previous workshops this year. We'll still be taking your questions live during the webcast, but we'll be answering them during the session, so please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. Now, we won't be monitoring the raised hand function, and I'll be posting relevant links in the chat window. We'll also be trying to answer as many questions as we can during the workshop, and we'll respond to any unanswered questions directly after the session is complete. Now, if for whatever reason you are having difficulty viewing the workshop live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. Okay, and with that said, I'll turn it over to Aya and Angela.
Thanks, Tom and Angela, and thank you everyone for attending the workshop. So today we are presenting live from our office in the Woodlands, Texas, and I'll be demonstrating CT data analysis. And what we're going to cover today include some basics of Fiji or ImageJ program, and we will do some CT image analysis. And we want to talk a little bit about next steps you can take if you decide to get into this a little bit deeper. The tool we're using today is ImageJ. And this is an open source Java program, and you can use this on Windows, Mac OS, and Linux. And there are actually a couple different distributions of ImageJ, and we are using Fiji. And this is the distribution I probably would recommend if you're going to use the ImageJ for CT image analysis. And again, this is available on all three operating systems. Now, you don't need to, but if you would like to, you can follow me and do the same analysis on your computer as well. And to do so, you will need Fiji already installed, and also Voxel Counter plugin installed on your computer, and downloaded sample data we're going to use today. And all of them are available from our website. And I think, Tom, you can maybe put the links in the chat. So if you don't have them yet or haven't done this yet, just enjoy the workshop, and you can watch the recording later to do the same analysis to give it a try by yourself. Okay, now let me switch the screen and let's get started. Okay, do you see my desktop?
You do.
Yes. Okay, thank you for nodding. So you have ImageJ already open, and this is the interface, and it might not look like much, but there is quite a bit we can do with this tool. And I also put the sticky note here so that you can see the shortcuts, which I will be probably using quite a bit today. But I will try to remember to show you where those things are in the menu as we go. Okay, so we're going to look at a couple different scans, but let's start with, let me open this folder, and let me start with this one. So this is a CT scan of a shark tooth. And by the way, if it's just a TIFF format, you can drag and drop it to ImageJ. You can always go to the file menu and open as well. And if you have a TIFF stack as the individual slices saved in one folder, you can drag and drop that folder into ImageJ as well. So this is a shark tooth CT scan. And when you load a CT scan, which has multiple slices in it, you will have this scroll bar at the bottom, and you can go through different slices this way. So we're just looking at 2D cross sections, but this is a 3D CT image. Now, using this scan, I will show you a couple of very basic operations you probably want to know how to do if you're going to use ImageJ for CT image analysis. And before we do any of the analysis, actually, Angela, let's ask the audience about a file size.
All right, so I'm launching the polling, and you should see the question. That's how big of a file can we analyze using ImageJ? So we'd like you to answer this question. Do you think it's 128 megabytes? Is it as big as the RAM size, or is it something that you set in ImageJ? We'll give a few seconds so that we have enough people voting, and lots of votes coming in. And a few more seconds, and I'll end the polling and then share the results with you. So polling is ending now. And it turns out that the largest votes were for you set it in ImageJ, second RAM size, and lowest 128 megabytes.
Okay, sounds good. I'm gonna say you got this one right. The majority of you did. So this scan I just opened is, by the way, is 256 megabyte, which you can see here. I'm sorry. I wanted to put the line underneath it. So you can see it here at the top of the window. So you can see it's more than 128 to begin with, but you probably don't want to open an image that is larger than the RAM size because it will slow down everything, but you can do it if you want to do so because you can set it in ImageJ. So to change the memory allocation, you go to edit, then options, then go to memory and threads. This is where you can set the allocated memory size for ImageJ. I think this number was a lot smaller when I installed it, but this is something you can change. And in other words, if this is set to be too small, you might get out of memory error. So this is something you want to take a look once you get the ImageJ. Okay. Now, one of the reasons why we asked this question at the beginning is that, as far as I can see it, ImageJ is a very widely used open source image analysis software, but it's not necessarily optimized to deal with a really large scans like CT scans in 20, 30 gigabyte file size, and the calculations can take a long time because of it. So it's important to pay attention to the file size, and if it's too big, it's good to know how you can reduce the file size. So that's the next thing we would like to show you. So before we do that, you might be wondering, this image is kind of dark, so you can adjust it by going to Image, Adjust, and Brightness and Contrast, or Control-Shift-C, and change the contrast brightness. You can click Automatic and set it automatic. You can also choose a certain area like this and set the brightness and the contrast adjusted for that particular area as well. So anyway, this looks a little bit better. Okay. Now, when you look at this image, let's go back here. You realize that the first probably up to 80 slices, it doesn't have the tooth in it. Now we have it. And it's the same thing towards the end. We have a lot of kind of empty slices. So we can get rid of the beginning and at the end, all those slices that don't have the tooth in it to reduce the file size. And to do that, there are a couple of different ways to do it, but probably the simplest way is to go to Image and Duplicate. And it will ask you what range you want to duplicate. So let's say, I think I need only 80 to maybe 460 and duplicate it. So I have another scan here. An original one was 256 megabyte, and this one has fewer slices and it's only 191. So I'm going to close this guy. The other thing we can do is to get rid of all the space around the tooth. And then when you do this, make sure that this yellow line, the cropping line, is not getting into the sample. So this might be a little too close. I'm gonna say this looks pretty good. Then again, you can go to image and crop. So now the file got pretty small. Let me make it bigger. I just did a Control+, by the way. So this is more efficient. We have everything we need and we just got rid of the parts we didn't need. Now, there is one more thing that you can do, not for all scans, but this particular scan has a very good contrast. So we can afford to go from 16-bit to 8-bit. That will reduce the file size. So let's do that by going to image type. You can see that it's 16. I can reduce this to 8. So overall, we started with 256 megabyte file, and now we're at 21. It's almost 1/10. So this will save a lot of space on the RAM. Okay, so now we have pretty, tight size file we can deal with easily. Now, let's do some measurements. So let's say we want to take a look at the size of the tooth. And to do that, you will choose this straight line tool. And you can draw a line where you want to measure the distance. Then go to Analyze and Measure. Then you see here, angle, this is the direction of the line, and also length. And it says 134.63. But the question is, what's the unit, right? We don't know what the unit is because we never set the voxel size or anything. So ImageJ really doesn't know what this is. Actually, it's counting the pixels. And you can see that just like the file size, you can see it here. So if you look at the top of the window, it says pixels. So this means that we don't know what this length is. So what we need to do here is to set the pixel or the voxel size. And to do so, we go to Analyze and go to Set Scale. This is where you can register the voxel size. So this one was 90 micron voxel size. So I'm going to say 1 pixel, that's the distance in pixels, is known to be 90 microns. So this is on how you can set the voxel size. This tooth is pretty big, so actually I'm going to go with a millimeter, so 0.09 millimeter. You can choose whatever unit you want and click OK. Then the first thing that changes is this unit. Now it's in millimeter. And if you do either Analyze and Measure or just Control M, then you get a new measurement that says 12.12. And this is in a millimeter. So this is how you can do simple scale measurements. Okay. Now talking about the scales, I think another thing you might want to do sometimes is to add a scale bar. And that's another thing that you can do just by going to Analyze. And where was it? It's in Tools and Scale Bar. And you can choose how long you want your scale bar to be and how thick or thin the line to be. You can change the color, let's say green, or the location. And you set all those things and click OK. And now you have a scale bar in your image. And once you do this, the scale bar stays on for all slices. Okay. Now, let's see. Oh, one more thing, actually 2 more things. We're looking at the cross sections, but we do have this 3D data. So you might want to look at the volume. And to do that, there are a couple of different plugins that can do 3D rendering and different cross section views. But we're going to use Volume Viewer today. And it takes a second and opens the Volume Viewer. So this shows you the 3D rendered view of the shark tooth. Now you can see the entire shape and you can align it to certain axis like this. Also, you have all three different cross sections to your left, and you can scroll through them as you like. And let me tilt this so you can see them. And you will see the cross section line shown as red or blue or green lines in this 3D rendering view as well. By the way, when you do this on your computer, it might look a little bit different because this plugin remembers what I was doing before. So the background color or the shading, those things could look different, but you can change all those settings at the top menu as well. Okay, so this is how you can look at the 3D rendering and the different cross sections. Right. The last thing I wanted to show you as one of the basic things you probably want to do is saving the results. So we reduced the file size and added the scale bar. So you might want to save this file as a new TIFF stack. And to do that, we go to File and go to Save As. And the simplest way to do this is just to go to TIFF. There are many different file formats, but this started with TIFF, so we're going to stick with it. And just give a name, and I'm going to save it in this results folder. And then when you save the image this way, let's take a look at the, not this one, but this folder. The results are saved as single file, which contains, tens and hundreds of slices. So that's one way to do it. The other way to do it, especially when the entire scan is a large file, you might want to save this in a folder as individual 2D images. And you can do that by the way, in ImageJ, always make sure that you make the window you want to act on active, then go to File. Then Save As, and in this case, you go to Image Sequence. And again, you can choose the file format and click OK. And this time I'm making a folder. You don't want to go up, make a folder, and let's say we're going to call this stack. And save the results in this folder. And then when you do it this way, let's take a look. You have a folder and you have individual 2D slices in it. So this is another way to save a TIFF stack. Okay. One more way to save results. So let's say that you want to share the result, this scan or the image, with a colleague that doesn't have ImageJ or any special tool to look at CT scans. Then you can save this image as a movie file. So you just choose AVI, and to keep the integrity of the image, you probably should do either none or PNG, but just for this workshop to save time, I'm going to choose JPEG, which changes the data. But let's set the frame rate as 20 and click OK and save it here. This is a convenient way to save scan if you want to share the results just quickly with somebody else. So let's take a look in the results folder. So you said that this is just an AVI movie folder, so you can play it on any computer without anything special. So you have the scale bar in it, and you have all the cross sections. Play it as a movie, or you can even go back and forth and look at different slices. So that's another way to save a scan. Okay, so those are the pretty much basic things you probably will be doing if you have a CT scan open in the ImageJ. But before we move on to different scans, let's see if there are some questions.
Yeah, we do. We've had a couple of questions come in.
Okay.
They're somewhat related. So the one is there any concern about viruses with the software, right? Because they're housed on public servers, things of that nature. Is there, is that a? I mean, I know the answer, but but I figure it'd be good.
So that's a good question. And disclaimer: I'm not an IT guy, but I talked to an IT guy in the office about it, and it is an open source. And also you can add, or anyone can add any plugins that would work in ImageJ. And I don't necessarily see a lot of regulations or control by the people who kind of, organize and manage this tool. So there is, I guess, a risk, at least technically, that somebody, might make something bad as a plugin, to do some damage to your computer. I've never heard of it. I don't know if this, including you audience, is an attractive target for hackers. Probably not. I think it's unlikely, but I cannot say that it's a very safe program. It doesn't make it any safer, and it is open to anybody to add plugins. So if you have any concerns, here's the canned answer. I would say that you should consult with your IT experts. And if anything, you can try this on a separate computer that's not connected to the internet to see if you're okay with it. But as far as I'm aware, I've never heard of anybody having any like a virus or problems with the program.
Okay. Okay. Then the second question, somewhat related, is there's a help that you can see on Fiji at the end of that toolbar. Are there user groups to help with this and so on?
So
just installation, and
it's a large community, people who use ImageJ. And I think, did I give you the link, Tom, yesterday?
I do have it. So
okay. If you can share it with everybody. Also, Tom is going to put a link in the chat for you to take a look at. And that's kind of ImageJ forum where you can go to and ask questions. And if whoever has the answer will see you and help you. And I find that website very helpful. And if you're looking for a certain thing you want to do and you can't figure out how to do it, actually Googling it helps. You don't even need to have a link to special forum, but if you Google, let's say, how to count voxels, ImageJ, and that will get you to a page that will explain it. And there's so many people who use this tool, and that's the beauty of it.
Yeah. And then one last question, actually all the questions are coming in now, is how was the tooth data obtained? How was that collected? Is that
okay, I should have mentioned, this was a scan on our Rigaku CT Lab GX X-ray CT scanner. And that's the machine we used. And I think I used the 90 kV setting in a probably 4-minute scan or so. And this is a system, by the way, that you can just place the tooth on the table and the X-ray source and detector go around it. So I didn't need to use tape or clay or anything in this case.
Okay, we have another
question.
Sure. Yeah, we have another question that I think we'll be addressing later with response, which says, can you determine the amount of aeration in the tooth? So that's kind of we're going to be talking about.
Yes, we will use a different scan, but you can quantify how much pores or air volume is in the tooth. Yes. Yeah.
And we'll be showing that later on. So to answer Robert's question, you'll see that shortly.
Okay.
Thank you.
All right. So speaking of that, so let's do that. Quantifying, let's say, the air volume. So I'm going to close this one. No, I don't need it. And go back to this folder. And by the way, what you're seeing here is what you will get when you download the sample data set. And we're going to go through most of them, but we're going to leave 2 of them to you as kind of homework for you to try on your own. So let me open those 2. Let's do this on a single cross-section first, just to keep it simple. Then I will show you how to do this in multiple slices, 3D form of a scan. So those are 2 images that came from bamboo tree. One image, this one, came from towards the inside of the tree. And this one came somewhere closer to the outside of the tree. And let me just adjust the contrast. The darker parts are air, and the lighter gray parts are the dry, woody part of the bamboo tree. Now, when you look at those 2 images, you can probably clearly see that the one from the inside, this one has more air than this one. It's amazing what our eyes can do, but let's see if we can quantify the difference. And to quantify the difference, in this case, either area or volume fraction, the first thing we have to do is to segment the images. Now, we have only two phases, air and wood or solid. So let's start with this one, and let's see if we can binarize this into just two phases. And to do that, go to Image, Adjust, and go to Threshold. In the Threshold dialog here, you will see many different algorithms you can use, and those algorithms do different math to pick where this threshold should be. If you choose a different one, it doesn't change that much, but this will move around. You can also change the threshold manually too, but because we want to compare two images, I think it's probably a good idea to pick one algorithm that gives you good looking results for both of the images so that you can let the algorithm pick the threshold so that the results are not operator dependent or image dependent. So let's start with default. And I think this looks pretty good. Air is all segmented and colored red. Now let's see if the same algorithm works on this one. So I'm gonna make this window active and use default. Now, I don't think this one looks great, meaning that I see a lot of red bits inside of the woody part. So default setting is probably not the best. So let me try different algorithms. I'm gonna scroll through them. Those don't look too different. This one actually looks even worse. This one, minimum, looks pretty good. This is pretty good clean segmentation. So let's say that I wanna use minimum as the binarization algorithm. But let's make sure that minimum works for this guy too, because we didn't test it. So again, I click this window to make it active, and the minimum is selected, and I click auto to pick a threshold, and this looks pretty good. Now, let's say we're happy with those results, so I'm gonna apply and then make this binarized. Now we have only black and white two phases. Do the same thing for this guy, and then we have only two phases. Now we are ready to do quantitative analysis. And to do that, you always go to analyze and measure, as we did for the length measurement. Then you realize that you get nothing, or you might get something, but not the area fraction. That's probably because you didn't choose that parameter to show in that window. So you can go to Analyze and Set Measurements and actually pick what you want to see in that window. So we want to see here is the area fraction. We're just doing this in 2D, so it's not volume, but area fraction. And I click OK. And again, make this window active, and I'm going to do just Control M. So now you have the number. For this image, the error is 43.89%. I think that sounds about right. Now I'm gonna make this window active and do the same thing, Control M, and get 17.74. So you see the results here. So this is how you can quantitatively compare the error volume in this case. Now, before we move on to the 3D version of this scan, actually, there was one more question that we wanted to ask the audience. So Angela, let's ask them the second question.
Okay, so question number 2 is, does the file have the voxel size information? So we'd like you to select yes, no, or we can't tell without checking Analyze, Set Scale. So everybody weigh in on their votes for this, and then we'll share the results. So quite a few votes coming in. We'll wait a couple more seconds for this, and then I'll end the polling and I'll share the results with everyone. So I'm going to end it in 3, 2, 1 and share the results. And the winner in this case was, we can't tell without checking Analyze, Set Scale.
Okay, so let's take a look. Generally speaking, you can actually tell if the voxel size is set or not by looking at the unit at the top of the window. So just to highlight it so you can see it, it's right here. It's tiny, but it's there. And if this is not pixel, but microns or millimeters, then most likely the voxel size is already set because TIFF files can have the pixel, in this case, size information in the header. But if you're not sure if this is correct, then you can always go to analyze and set scale to see what was set. And if that's incorrect, you can change it there. Okay, so when you're doing a volume or area fraction, by the way, you don't necessarily need to set the voxel size because you're just looking at the ratio. But we thought we would ask this question at this point. Okay, so let me close those and probably this too, and open another bamboo tree scan. So this is a little bit larger scan, and let's make it a little bit bigger. Okay. It's still not the entire image. There you go. That's about the whole image. So this is a 3D volume, and you can see that here, you can go through different slices. So this is a 3D volume, and the voxel size already set. You can see it at the bottom, and we have 624 slices in this image. Let's set the, so in this case, I just clicked the auto, and because there are very bright spots at the right bottom corner, it set the scale very, not scale, but the contrast and brightness very dark. If you don't like this, you can just avoid the bright spots and do this, and it works better. Okay, so let's see if we can quantify the error percentage in this image. So to do that, again, we will do thresholding. Okay, and in this case, minimum does not work at all. So let's go back to default. That was ugly. And I think this looks pretty reasonable. But when you have a 3D scan, always go through different slices to make sure that there is no surprise. And I'm gonna say this looks decent. Okay. If you like this, you can click apply. And when you have a stack with multiple slices, you get additional window looking like this one. And choose to calculate the threshold for each slice, each image, or use one number for the entire volume. I'm gonna calculate it for each image. And if you check list thresholds, then you will see what the threshold was for every single scan. So let's see what we get here. Okay, so it's binarized. You can see that the entire volume is now, it's all just black and white. And you see the results here, meaning the thresholds. And it's about 100, 101. And I don't see any two different number. So I'm pretty happy with this. If you see a number, the threshold that is completely, out of the norm, or different from other slices, you might want to go to that slice and take a look at it to make sure that nothing went wrong. Okay, so now we binarize this 3D volume. So we are ready to do the error percentage calculation. Now let's go to analyze and measure. Then you get the percentage here. Now, I don't know if you noticed this, but it says area percentage, not volume percentage. And this is because this is an area percentage just for this slice. It says 37.16. Let's say I go to a different slice and do Control M, then I get a different number. So those are just for each slice. It's not the entire volume percentage. To get the entire volume percentage, we need to count the total voxels. And that's where the plugin we mentioned at the beginning, the Voxel Counter, comes in handy. So to use the Voxel Counter, I already installed it, so I can just go to plugin and use it. But just in case you've never done this before, let's ask the audience the third question, Angela.
All right, so our question in this case is, how can we add plugins? So would you execute the plugin installer to add the plugin? Would you copy and paste the Java source code into the ImageJ source? Or would you copy the plugin file to the ImageJ Fiji plugin folder? And we'll give a few seconds to get everybody's vote in. And it's pretty heavily leaning one way. So I'll just leave a couple more seconds, and now I'll close the voting and I'll share the results. So the winner in this case is to copy the plugin file to the ImageJ plugin folder.
Yes, that is the correct answer. I think everybody's getting it right collectively, got all the questions right. So this is a portable program, and there is really no real installer to run, even for the ImageJ itself. And it's the same thing for plugins. When you want to add a plugin, you download the plugin file and add it to wherever you put ImageJ folder. Go to that folder, then put the plugin file under the plugin folder. Then restart the ImageJ, then you will have it. And I mean, you will have it in this plugin menu. So let's use Voxel Counter to calculate the volume percentage. So I'm going to make this window active and then go to plugins and go to Voxel Counter. There are many things in this menu. This is only I, but they're all ordered in alphabetical order. So I'm going to go to this one, and it's going to do the calculation. And there we have the results. So what this plugin does is it's going to count the percentage or calculate the area for every single slice for 600 something to go through the entire volume, and it will give you this volume fraction at the end. So it's not too far from what we got from individual slices, which makes sense. But for the entire volume, this is how you can calculate the percentage of the air. In this case, it's 39.19%. Okay, so I think we did everything we wanted to do for bamboo trees. Yeah. Let's see, are there new questions, Tom?
We have had a couple of questions come in.
Okay.
First one is it possible to remove, describes it as noise dots. I think it just means noise, right? From an image in both the view and in the statistical calculation. So it's kind of a, can you erase almost like a bad pixel?
Depends on, I guess you can just treat them as bad pixels or noise. You know, those little bits you see here and there, right?
Yeah.
So we will address it a little bit in the next scan in terms of reducing the noise level for the original image. So that's one, if you can do that with the original image before you do the segmentation. So that's one way to reduce those dots or noise. Once you do the segmentation, then you want to reduce those little dots. You can probably do the same noise reduction. You know, those are averaging programs, so you can do that. I'm trying not to give away too much for the next question, but
yeah, exactly. I know. It's a leading question. It's a leading question. So,
but after the segmentation, another thing you can do is a morphology operation, meaning you can do a close, open, or dilate, erode. Those are the shape operation function. You have this, you know, big of a black circle, you know, on your image, and erode means that you will do calculation to make it smaller, or you can make it dilate. For example, if you do those two to one after another, you don't change the original size, but if this guy is really, really tiny, when you erode it, it will disappear. And then when you make it bigger again, it won't show up. And that'll, the combination of those two operations will get rid of most of the single or a few voxel bits. And you can do it on an ImageJ too.
Okay, we do have another question, but I've asked for some clarification, so we'll come back to that one.
Okay, okay,
And we can do that towards the end. Okay.
all right. Now, so let's take a look at the next scan. We have this is a scan and we have a noise problem. Okay. So if you were with us in the last workshop for Dragonfly, this might look familiar to you. So this is a CT cross-section. We're going to just look at one cross-section first, then we'll do 3D. So this is a CT scan of a foam or earplug, and dark gray is air and light gray is the polymer. So again, let's say we want to separate those two phases and quantify their volume, for example. If I just use regular thresholding to segment those two, you get something like this. This doesn't look too good. You know, you have the gray holes in the air and also red bits inside of the polymer. You can change the algorithm, but the thing is, no matter what you choose, it's not gonna look too good. And when this happens, the first thing you can try is to manually adjust this. So let's say that I'm gonna try to close those gray holes. And to do that, I'm gonna shift it towards right. And by the time I close all those holes, most of the polymer is selected as well. So this is not gonna work. And if you try to clean the polymer part, then I have too many holes in the red part. So you can see that the threshold is not working very well. And this is where we wanted to ask the next question.
Okay, so launching polling again, and the question is, how do we improve these thresholding results? So what could we do? Could we apply a smoothing filter? Could we apply an FFT? Or perhaps could we apply edge detection? So we want you to pick maybe with a strategy you might try, and then we'll do that. Okay, so we're getting quite a few votes coming in. Give a few more seconds. We've got over half of the people in voting, so another couple of seconds. I'll end and I'll share the results. So in this case, the lead vote was for applying edge detection.
Okay, it was close, right?
It was very close. Second,
apply smooth filter was close to. Okay, so let's try edge detection. So I'm gonna reset this for now, and then go to make this active again, and then go to process, and there it is, find edges. So if you apply it, then you can see where the border lines are between two phases. But when you come back and do this thresholding, now you're binarizing this image into the border line and everything else. So this is interesting, but not quite what we wanted to do. So what else can we do? Reset. So I probably should have duplicated the original image because I want to do something else, but let me open it in a separate window. So this is the edge detection we tried. This is the original image. Now, the problem we're having here is the high noise level. And I'm going to give away the answer now. Smoothing is one of the things you can do, because smoothing is, in other words, noise reduction. So if you don't do anything, you get something like this. Now let's see what happens. Let me close this one and duplicate this too. So got original saved here, and this is the one I'm going to work on. You can go to process and choose just smooth, but this one doesn't give you a lot of choices. So instead, I'm going to go to filters. Then you will see a lot of different kinds of noise reduction or smoothing filters you can choose from. And It's a bit of a trial and error to choose the right one, but median is probably one of the most commonly used smoothing filter because it's good at preserving the edges. So the default is radius 2.0 pixels. If you check preview, then you can see the preview applied after the application of the filter. And I'm gonna say that I wanna be a little bit more aggressive to make sure that we get rid of all the noise. I think this looks pretty good. I'm gonna click OK. And you see that this is original and this is a smooth one. And the borderline between two phases are still there. They're not blurred too badly. So now let's try thresholding with this one. There we go. So this is not bad. It's not perfect. Let's compare it here. So compared to what we had before, this looks a lot better. So noise reduction or smoothing is something you can try when you have a very noisy scan. Now, you might be wondering, isn't there a better way to do this? Or didn't you do machine learning the last time? And we did. And you can do machine learning as well using ImageJ. So that's the last thing I would like to show you. So let me close this guy, the one we smoothed, and we come back here, and I don't need this one anymore. So if you're going to use machine learning to segment this image, again, we go to plugins. There is a plugin you can use for machine learning, and it is under segmentation. And there are a couple different versions, but I'm going to use this trainable Weka segmentation. And it takes a few seconds to open it. And this is the Weka interface. So you have the image you want to segment, and you see labels as class 1 and class 2 here. And you're going to have more than 2 classes, by the way. But those names are not too good. So let me go to settings and change their names. So we're looking for 2 phases, air and let's say polymer. Okay. And you can change those names. When you use machine learning, the way it works is you as the analyzer show an example of what air looks like and what polymer looks like, or how you would segment this image to the machine and let the machine learn how to do it and do the rest of the work. So the first step is to show it the example. So I'm going to choose the circle one and say, this is air. You just click add to air, do the same thing. You do it for a couple different patches, and this is polymer. So I'm going to add this to polymer. Then always getting the borderline part between 2 phases is very important. So I'm going to zoom into, let's say, this area, and I'm going to use this freehand tool. And it doesn't need to be perfect, but do your best to kind of trace the borderline and say, this is air. And on this side, we're going to get, I'm running a little over, but that's okay, do polymer. Okay. So now we have a couple patches, to use for training. And at this point, you can go ahead and start the training. So I'm going to click this one, train classifier, and the machine is going to look at what you just did and try to do the same thing for the rest of the image. It actually doesn't take, okay, it's done. So I would say this is a pretty clean segmentation, and I don't see too many red bits. This is probably real. This is the beginning of another pore. And this is polymer. They're not mixed, so it's pretty clean. And it might not go this well for the first try when you have more challenging scans. Then you can always retrain the program. So let me show you an example. I'm going to zoom into this area. And let's say that I think that this red is bleeding out to green. It should be a little bit smaller. Then you would simply make a correction like this. No, I think that this should be all green like this. Then train it again. And you can go through multiple steps. So you see that the red shrunk a little bit. So machine is learning from the mistakes you pointed out. And by repeating this process, you can get pretty decent results like this. Now, when you do a CT scan analysis, do this segmentation for 3D volume, you will have multiple slices. But to kind of shorten the calculation time, I think it's probably good to pick a typical cross-section like the one we're looking at here and train it using this cross-section. Then you can save that classifier you just trained. So I'm going to click Save Classifier and save it in this folder. Then apply that classifier to a larger file that is 3D. That's what we're going to do next. So this was just one slice we used for training. But now I'm going to open this one. So this is the same type of foam, but this one is 3D. We have multiple slices. And what you do is the same. You go to Plugins and Segmentation and Trainable Weka. And you go back to the same interface. The difference is you have multiple slices in it already. And we have the classifier already saved, so we can just load it. And it takes a few seconds. Okay, so it loaded the classifier, and all you have to do at this point is just to click Create Result. Okay, I think that this will take a minute or two, so let's take a couple more questions.
Yeah, so actually this is a good one, is can we apply different thresholds to different slices of a 3D image?
Yes, you can do it one by one. And also, even if you use automatic thresholding, you can choose to use the same threshold across multiple slices or recalculate the threshold for each slice. You can do it either way.
Okay. All right. And then another question here, and I need to read the original. So what if we need to count the high density particle instead of the air pocket? So the question is with respect to a composite with particles in the matrix. So it's kind of reassigning what the volume area is, perhaps.
Right. So the darker part was being calculated in this demonstration, but you can, I think there's a checkbox that says dark background or either a light background. There's a checkbox to check to flip black and white.
Okay.
And that way you can calculate the volume fraction of the lighter part, not the darker part. So you can do it either way.
Okay. We do have a few other questions. We'll let you wrap up here, and then if we have time, we'll get to those at the end.
Okay. So it took a little while, but you see the results here, and I'm gonna go through different slices. So you see that this is pretty clean segmentation, and we were successful applying it to 3D volume. So if you have a little bit noisy image, or for whatever reason, the thresholding based segmentation is not working very well, you might have like a 3, 4, 5 phases, then this Weka segmentation plugin is a very, very powerful tool you can use. The only thing to keep in mind is that the calculation can take a long time. So be patient and also minimize your file size. Okay. So let's go back to the PowerPoint slides. Flip the page one. So although ImageJ is a powerful tool, and no one can complain that it's open for anybody and free, but if you feel like you need a little bit more, you need a more powerful tool or something faster, fancier, then there are different tools you can use. And also, if you're interested in learning what all those operations are doing, like a medium filter, what is it actually doing to my data? And there are a couple of different places I would recommend you can learn what's going on math-wise behind the scenes. So one is this, I'm going to call this a shortcut to learn what data analysis is for X-ray CT. This is one of the webinars we did 2 years ago, I think. There is an episode about CT data analysis. It's about a 1 hour webinar, but we go all the way from what a histogram is and what thresholding is and what all those morphology operations, smoothing are, and all the way to machine learning and deep learning, like everything squished into 1 hour. So you might find, if you're new to this, especially, you might find this one useful. And we have the link in the chat, I guess.
We do.
Thank you. The other one we would recommend is this is a YouTube playlist or series by Professor Rigaku. And he, I suppose, recorded the entire lecture he did about digital imaging, image processing. And I highly recommend this one if you want to learn what image processing is and how it's being done. He uses MATLAB to demonstrate all those image processing. So this is another one I would highly recommend. So those are the places you can go to learn a little bit more. As far as the tools go, Dragonfly by Object Research Systems and BG Studio by Volume Graphics are the tools we use most of the time. Angela and I use those too. There are many other different tools kind of similar to them. But those are the commercially available tools you can use for more complicated analysis and also faster calculations. And you might be wondering, so what's the difference between the two? Generally, I think Dragonfly would work very well when you're looking at material science type of images, like a foams or plants or composite materials, insects, because the segmentation can be very challenging for those materials in life science samples. And Dragonfly has a really good deep learning module you can use for them. If you are doing, on the other hand, more of a dimensional analysis to measure the sizes of things or comparing the results to CAD drawing, then VG Studio by Volume Graphics, I'm gonna say, is almost a de facto standard in the industry to use. So those are two other tools you can use. Okay, so you just learned some basic operations using ImageJ, and we did some CT image analysis and talked about a couple of next steps you can take. And not too much, but I think we have a few more minutes left for questions.
Yeah. So we have just a couple of questions, so we'll ask them real quick. The one was with reference to the Bamboo 3D. We were looking at the Z-axis was one of the questions. It appeared as though we were looking at the trends, the image going up the Z-axis.
Right, so the one cross-section you saw at a time was the XY plane or cross-section. And
Yes.
when I did the scrolling, you're going back and forth in the Z direction.
Okay.
At least that's how normally XYZ are defined.
Right. Okay, and we have one additional question, and it's can we do particle analysis, getting the size of each particle or feature in an image?
You can, and it might be just that I was never able to find it. So if anybody in the audience knows how to do this, let us know. But you can definitely do particle size analysis. There is even a menu you can go to for 2D images. If you have those particles in 2D scan, ImageJ can measure their sizes and calculate the distribution and everything. But I was not so far able to figure out a way to do this in 3D.
Okay. All right. So that's all the time we have for questions, as we're getting right on to an hour here. So we do have a couple additional questions. We will get back to you directly after the webinar. Now, as I said earlier, a recording of the workshop will be available tomorrow, and an email will go out to all registrants with instructions on how to view the recorded presentation. I just put up a link to the quick reference guide. You've seen some of those from our previous workshops, as well as a link to the previous workshops and registration for our future workshop. So these links will also be shared in that email on the landing page. So we'll be hosting another interactive workshop focusing on micro CT data collection techniques on Wednesday, July the 14th at 2 p.m. Eastern, 11 a.m. Pacific, and we look forward to seeing all of you then. Thank you for joining us, and we'll talk again in July. Bye-bye now.